I'm going to talk about JVM profilers and how they work, how they like us, etc. I work, oh, right, before I even start, I generally like to thank people for coming, and if they leave, that's okay, but thank you for making the effort, and thanks Theo for organizing this first Java conference. I know it's been an uphill battle with some of the details, so great work. Right, I work on Zing. Has anybody here heard of Azure Systems, Zing? Does that mean anything to anyone? All right, we got like a few people. We produce a great JVM. It's the best JVM. I only say that because I work there. But it is a great JVM. Only works on Linux, only works on x86, so Intel AMDs. Aimed at server-side systems, obviously. And we are focused on responsiveness. We're focused on eliminating all the pauses that you get with Java. A lot of people consider those like inherent flaws in the JVM. They're not inherent, they can be eliminated, and they are eliminated. With Zing, it sounds like a load of marketing material, but it does actually work. So if you are suffering from GC pauses and you spend your life tuning that away, you can stop doing that and just pay for a license, which is quite reasonable. Okay. Apart from that, I fail to format my slides on occasion. But when I don't do that, I write a blog, which is sort of moderately sort of successful. I work on a lot of open source projects, mainly JC Tools, which is a lock-free Q library. That sounds quite exotic, but actually there's every chance you guys are using it under the hood anyway. Netflix are using it, Netty is using it, which means that if you're using Cassandra, you're using it. I started working on Aaron and Agronomo, which is sort of a low latency messaging library, and I've contributed to loads of little projects here and there, and there's the whole Cape Town Java meetup thing going on. Right, we're going to talk about profiling. The first question you got to ask yourself is, why do you profile at all? Some people profile because they want to be much faster. This is, by the way, not me. This is not my other career. This is Vin Diesel. So people profile, surprisingly, not when they want to go fast, but when they realize they're going slow. So profiling is part of the sort of problem analysis. Everything is falling around our heads stage, but it doesn't have to be. You could proactively profile your application. The other reason, I love this quote, it's completely unrelated to anything, but basically it's sad when you have a load of illusions about what you do and how stuff works. So if you think you're going to show someone something you built and it's not what you think it is, it can get quite embarrassing. Happens surprisingly often to a lot of very qualified people. So you make a change, you think it made stuff better, but it actually made stuff worse. If you actually tested it, profiled it, made sure that you're changing the right thing in the right place, that you wouldn't get taken away to an institution, right? This is a survey done by Rebel Labs. They make a profiler, but more importantly, they have the best graphic designer. So every report they print looks just awesome. So I borrowed this slide from them, and you can see what people think, like any survey, what's their impression of where performance problems come from. So you have here in the middle, I'm not going to use the pointer because it might kill the thingy, but you have like slow database queries, too many database queries, which sort of plays to what Andreas was talking about yesterday. But you also have this big blob here on the, bottom right, where there's inefficient application code. Inefficient application code will show up in the profiler, so that's what you'll use the profiler to diagnose. Which profiler you use is a different question. Is anybody here used a profiler at all, ever? Right, loads of people, that's great. So this is what people say they use. Let's see if we have sort of a correlation. Who's here used JVisualVM? Who's used Java Mission Control? All right. You should all try it out, really. It's pretty good. YourKit, any YourKit users? See, more YourKit, you actually pay for stuff, and Java Mission Control is great and for free. At least on your desktop, right? We've had the people who don't use anything, and then there's the people who don't know which profiler they use, which also happens, I guess. Interestingly, perhaps, JVisualVM and NetBeans Profiler, they're the same profiler, so it actually dominates the market, I think because of basically history. It's been there forever, so that's what people use. I'm going to be talking about sampling profilers, which have nothing to do with primates or monkeys, but are quite confusing to people. I believe Andreas's profile he mentioned yesterday, DownTrace, it uses a combination of techniques, so this doesn't necessarily apply to a particular profiler, but we'll talk about several sampling profilers and the APIs they use and the behaviors they tend to have. Just an introduction to sampling profilers sample the program on an interval, so we take a snapshot every once in a while. The distribution of samples highlights hotspots. That's the basic assumption here. So how does that work? We assume that the samples are representative, so the samples are arbitrary or random. That means we choose when to take the sample, not the application. Similar to how, if your manager samples your performance, if he only sampled you this all the time, then they'll get a very bad impression of what you're actually doing. And the sample distribution approximates the time spent distribution. This is important about sampling because it is an approximation. We're taking snapshots of the behavior, so we might miss something. We want to approximate the real behavior by taking a lot of snapshots and then finding out what actually happened. This is the simplest profiler you can build. It actually works. Uses JStack that Rudolph mentioned yesterday. So runs in a loop, sleeps for an interval, and collects the stack. We're going to have a look at that just because it's nice and simple and gives you a bit of context. But for that, I would have to find my shit. See, this is what happens when you use an open source distribution. Okay, right, we're going to have a benchmark to run. This is a benchmark I put together. We're going to have a look at the code just now. I'm using JMH. Has anybody here used JMH before? Anybody heard of JMH? All right, if you're doing any sort of hand-rolled benchmarking, cut that shit out and start using JMH, which would save you a lot of embarrassment and probably a lot of work as well. So JMH will spin up the benchmark and start running it, taking lovely measurements as it goes along. And in another window here, we'll just do JPS, which finds all the Java processes, and then we'll call JStack on forked main, which is where the benchmark is actually running. Shove it into less, because we're going to get loads of crap coming out. Right. And there we go. This is what a stack looks like. When we look at it, see hash map put on the top, which is appropriate because the benchmark is called hash map put is to blame. And then we have all the methods underneath it, which is the call stack. If you've done any sort of OS course, or if you've ever looked at a profiler or did a thread stack trace or caught an exception, you've probably seen this before. It's all the calls climbing up, and at the top is the method that's actually executing. Profiler will typically collect lots of call stacks and sort of layer them together to give you an execution tree to look at. So that's great, or at least, informative. Let's go back to this. I tell you, I had it all set up and then I had to sort of resize everything. Went to shit. Okay, right. So that was a very short demo, just to give people an idea what the call stack is. So when we're looking at sampling profiles, we imagine this web server thread run thing is running in the background. the x-axis is time and the y is the depth of the stack. And we can see loads of methods, and the theory is with a sampling profiler we'll hit the application every once in a while and we'll collect lots of different stacks, and that will give us an idea of what's happening most of the time. And as you can see, we'll miss some things because we're sampling and maybe something sort of fell through the cracks. And the idea is if we do it for long enough, we'll catch everything that's really happening a lot, which is what we're interested in, right? The code that's taking up all our time. Problems with sampling, not enough samples. If I take 3 samples, that's not really representative of anything that's going to happen in my application. I need to take loads of samples to approximate what's happening, like any approximation. So either you switch to a tracing profiler, which will trace everything that you do, and then you can do an operation just once, and it'll sort of log out everything that you've done, or have a shorter sampling interval, so you sample 100 times a second. Alternatively, just hang in there and wait, and the samples will come. Another problem, which is half theoretical, is the periodicity bias, which means I sample at an interval that matches the application's life cycle. Doesn't really happen when we have short intervals, but if I was to sample an application once a day at midnight, there's no web traffic, nobody's coming to the website, I'll get the idea that the application is doing nothing all the time. If I sample every hour, maybe there's an hourly sort of cycle. If you're sampling 100 times a second, it's probably not a problem, but people like to hang on to it. So shorter intervals will sort that out. You can randomize the interval to sort of play around and see that you're not falling into some sort of routine that matches the application. Another problem is when sample taking is expensive. So if I take a sample and I slow the application down, whenever I do that, that might not be acceptable. So either I switch a sampling method to something that's cheaper, I learn to accept the overhead. People who use profilers in production tend to just learn to live with a certain overhead. And it's okay for if a profiler is useful, and it has a 1% sort of overhead on top of your application, a lot of people will happily accept it for the extra monitoring and analysis capabilities. You can't get something for nothing. Every profiler will have some overhead, so you have to find an acceptable balance. And one way to do that is to have a longer interval, so you don't sample as often, you don't pay as often, the overall impact on your application is going to be reduced. So if you're using a sampling technique that's very expensive, maybe you shouldn't sample 1,000 times a second, maybe once a second will be fine, just wait a little longer. Last one is a bit unfortunate, right? The sample is biased or inaccurate, so the measurements are not random. You can switch sampling method to something that's less biased. You can widen your scope, and this is important. Maybe you have some sort of technique that is flawed. That doesn't mean it's useless, right? You can learn to accept that the tool isn't perfect and look slightly on the sides of where it's pointing you, and maybe you'll get something useful. So the problems with the Java, the sampling little script thing I put together, or JVisualVM for that matter, it reports all the threads, running or not. So you saw the stack I was getting, but I was getting all the stacks for all the threads. So I'm paying for all the threads in the application whenever I'm taking a sample. It uses GetStackTrace, which I'll explain in a second what that actually means. But GetStackTrace has a high overhead. It is safe point biased. Who here knows what a safe point is? Right. Nobody ever knows what a safe point is, for good reasons. We'll get to it in a second. Right. So what's GetStackTrace? GetStackTrace is part of the JVM TI. JVM TI is part of the JVM specification. So every JVM on the planet has to implement it to be called a JVM. So if you're implementing a commercial profiler, like YourKit, like JProfiler, like DynaTrace, you will use JVM TI and you will use this method because that's guaranteed to work with JVMs, okay? And the API looks like this. You give it a thread, you can give it a bunch of threads and get all of them all together, and it tells you if stuff didn't work out for it, but if it did, it tells you what the J method ID is, which is sort of self-explanatory. There's an ID for a method, or it gives you J location. J location is surprisingly not where Jennifer Lopez is. It's nothing to do with her, in fact. But instead, it means BCI. BCI is the bytecode index. When we compile Java code, we get bytecode. So perhaps surprisingly to some of you, the server doesn't sit there and read through your code and executes the text. It doesn't even see the text, it gets the bytecode, right? It gets compiled classes. Some bytecode is actually generated on the fly if you're using Spring, if you're using other sort of bytecode manipulating frameworks. And so the bytecode index is where in the method are we in relation to the bytecode. Okay, so not every BCI has a line of code, so we find the closest. We could look at the code that finds it, but actually it's trivial. You run through a table of lines of code, and each line of code has a BCI, and if you're close enough, then you'll say it's probably that line. Okay. GetStackTrace samples at a safe point. Let's explain what a safe point is. Confusing though it may seem. Safe point is a JVM thread state. A JVM thread, by that I mean, any thread inside the JVM process. There's loads of threads flying about, right? If a thread is waiting or idle or blocked, it's at a safe point already. Haven't explained what a safe point is, but it's there. Okay. If it's actually running Java code, if it's executing instructions that you want to execute, it's not at a safe point. Okay. If it's running JNI code, which is instructions you want to run, but it's not Java, then it's at a safe point. It gets parked at a safe point before you go into the JNI call. Something very obvious here. When you're sampling at a safe point, you're not actually sampling Java code running, because if it was running, it wouldn't be at a safe point, right? So what is it that you see there? At a safe point, this is a quote from Gil Teller. He's the CTO, is my boss of Azul, and he is very eloquent, so I just cut and paste what he said. And the thread's representation of its Java machine state is well described and can be safely manipulated. It's another way of saying safe points are an implementation detail of the JVM. You won't find them in the language specification, you won't find them in the memory model, you won't find them anywhere. And why most people don't know about them is because they're not part of the Java language. They're just a convenient way to put stuff on hold and fix it up like you would when you do a garbage collection or recompile a method, and then let the thread go again. So it's a matter of convenience, it's an implementation detail, but all the JVMs do it because it's, makes stuff possible. So how do we bring a thread to a safe point? How do we stop a running Java thread from executing, stop it safely so we can manipulate the heap and let it go again? We raise some sort of safe point flag. The thread has to notice that flag is up. We don't just interrupt the thread that's running. The thread has to come to the safe point. The safe point doesn't come to the thread. So the thread transitions to a safe point state, and then we can manipulate it. Where do we see a safe point pool? Between two every bytecodes if we're in the interpreter. Anybody here knows the difference between interpreter, C1, C2? Raise your hands. Difference between running an interpreter versus compiled? Okay, I'll explain. You take your bytecodes and now you want to run them on the JVM. The simplest way to run the bytecode is to go through some sort of interpreter, which is sort of like a big state machine that says, here's a bytecode, what should I do? You should do this, get back, and then continue through that sort of state machine. That's very inefficient. So the JVM takes your bytecode and compiles it on the fly, the whole just-in-time compilation thing, into machine code that's appropriate for the machine you're running on, which is a great thing that the JVM does. There's two compilers predominantly. There's C1, which is the client compiler, which is a cheap compiler, so it doesn't take a long time to compile your methods, but it's not very high quality. There's the C2 compiler, which is meant for server long-running applications, where you would spend longer time producing compiled code, but it would be highly efficient. It would do all the optimizations, and life would be great once it happens. So your hot code will probably be in sort of the C2 compiled state, okay? In C1 or C2, so compiled code, you won't get a save point between every 2 instructions because that would be too expensive and too wasteful. So it's on the back edge of non-counted loops, which is whatever the JVM considers to be an infinite loop. On method exit or method entry, depending on the JVM. And when you come back from JNI, the reason you have a save point pool when you come back from JNI is because maybe the JVM stopped all the threads and you just didn't notice because you were running your native code. So when you come back, say, is everybody running? Can I keep running? No, yes. Then you keep going. So if we look at a method here, we have some code, we have an integer sort of indexed loop, and then we have a while loop, and then we exit the method. This is what it looks like to us with the naked eye, but if we could see save points, this is where they would be once the code gets compiled. Save point bias means I'm not going to see anything that's not near a save point. So all these little methods that are in do something, they all got inlined. When I inline the method, I remove the method in fact. So there's no save point to be had when I exit the method because the method is no longer there. I inline the code. Okay, I only see the end of controller do something because all of these other methods effectively cease to exist as far as a save point profiler is concerned. It's just a harmless little save point. I said, everybody here seen the Holy Grail, right? So to you, this is funny, and to me, and we're having fun. Everybody else, screw you, hey? Right. So this is what happens when a profiler hits you with a GetStackTrace. We have loads of threads, right? J1 here was asked to, stop at a save point, and it just stopped. It's a nice thread. It really listens when you tell it to stop, right? J2, J3, not so good. Maybe they're contending over a CPU, and they can't make it to the save point because they need to actually run some instructions to get to the save point. So we can see J3 maybe pushed J2 off the CPU and then stopped, and then J2. J1 was waiting all that time. So as far as that thread is concerned, we spent a lot longer doing GetStackTrace. Okay, this is not a fair sort of operation. We're not stopping everyone. They just all stop together and they all experience the same kind of pause. Okay, we're seeing a long, this is called time to save point, or TTSP as people like to shorten it. We also see the JNI threads. J4 is running in JNI and just doesn't care about this whole thing. J5 tries to come back halfway through the save point and then it gets stopped. Okay, so the world is slightly more complex than just stopping one thread. We're trying to stop all the threads. We're doing a stop the world operation. Okay, so this is the overhead for GetStackTrace on OpenJDK. You have to stop all the Java threads. OpenJDK has a very simple save point mechanism, which is a global save point. If you want to stop one, you stop everyone. There's a special page, you set it to protected, everybody gets a segfault, and the JVM just handles it. Big overhead, but very simple and very low cost when save points don't happen. Okay, and then you collect all the thread call traces, and then you resume all the stop threads. One of the problems with this approach, and I think JVMs are going to hit on it more and more as we move into the future with lots of processes. If I have 100 cores, 500 cores on a server machine, and this is not science fiction, this is happening today, stopping 500 threads and resuming 500 threads is quite a lot of overhead for something that is potentially quite a small operation inside the save point. When we had servers with 4 cores, less of an issue. So I think there's going to be a lot of emphasis on this going forward. On Zing, we have the thread level save point, so we can collect a single thread call trace without stopping all the other threads. The reason Zing is more focused on this sort of problem is because Zing used to run on its own hardware, and we had servers with like 750 CPUs 8 years ago, and that was the hardware we were deploying on, so this became a problem for us a bit earlier than for Oracle. Right, let's have a look at what does the save point bias do to us. Okay. So this is what happens when you do a live demo, right? Worked perfectly last week, and now it's like, yeah, whatever. Okay. We'll get to that perhaps later when I have time to sort my shit out. Let's stop this. Okay. Right, there's two things I wanted to go through, but with the whole shenanigan, it just didn't work. There's two elements here. When you profile and you collect the stack from all your threads, the more threads you have, the more overhead you have. It didn't quite work out, but trust me, this is how it works. Well, you don't have to trust me, you can try yourself. And the other thing is, the more, and that's hard to demonstrate on a laptop, the more running threads we have, the longer it's going to take to get to a save point. I'm not going to go into it because I'm sort of running out of time with faffing around here. So there's a flag you can enable to see what's happening with time to save point. I might demonstrate it in a second, but let's move on. So there's an alternative API where we're going to look at profilers that use it. Called AsyncGetCallTrace. AsyncGetCallTrace is not an official API. It's not part of JVM TI, which is why commercial profilers don't use it. Some vendor profilers would use it, such as Solaris Studio, such as Honest Profiler, which is not a vendor profiler, but it is an open source one, and relies on it because it only targets the Oracle JVM basically, and Java Mission Control uses it. That means these profilers won't have the sampling bias. It's built for sampling in a signal handler. That's also quite handy. So what you do is what native profilers have done all along. You interrupt threads that are on core, and then you run your signal handler code and collect the stack just for that. You don't stop the whole process just for the sake of collecting a stack trace. Doesn't require a save point. Only samples the interrupted thread. This is important because threads that are off CPU, if you have a lot of contention, everybody's sort of in the run queue, you're not going to see them. You only see what's actually being run. Again, doesn't need to be at a save point. So the process now looks like this. You get a signal, you run the interrupt handler that you've written to profile, and GetStackTrace collects the profile. Everybody else keeps running. Okay, another signal comes along, another thread gets interrupted. You only collect from one thread, you don't see the save point bias, which means there's a lot less overhead to contend with, and the sampling is more accurate, one hopes. So who uses AsyncGetCallTrace? Solaris Studio. Solaris Studio is one of those tools that nobody uses. You didn't see it on the slide with all the profilers because only Charlie Hunt uses it, who's the profiling guy from Oracle. The reason nobody uses it is because everybody thinks it only works on Solaris. But it actually works on Linux as well. So you can use it. It's a great tool, but a bit complex to use and hidden very well. There's Java Flight Recorder or Java Mission Control, which I really recommend people have a go at using it. And there's lightweight Java Profiler and Honest Profiler, which are sort of tools that are evolved. Honest Profiler evolved from the lightweight Java Profiler that came out of Google, and also relies on that undocumented API to get the samples. It's a bit ghetto. We'll have a look at how it looks just now. Okay, let's try this live demo shit again. See how that goes. Okay, so I was going to show you just a second ago before I gave up on this whole. So there's a flag here, print GC application stop time. I imagine not many people are familiar with it. When you look at your GC logs, the GC log said I stopped for 5 milliseconds. What it's not telling you is that maybe it took it 100 milliseconds to stop. So the GC pause doesn't include the time to save point. If you add this flag, you can see here that stopping the threads took, whatever, 6 milliseconds. What we wanted to do in the save point also took 6 milliseconds. So the delta between these two is what I actually wanted to do at the save point. So if stopping the threads took, very little, so 38 microseconds, and what I wanted to do at the save point took, say, 50 milliseconds, that makes sense. I don't want to spend all my time stopping threads and then doing no work at the save point. When I stop the JVM, there's probably a good reason why I want to do it. I don't want to spend all my time bringing everyone to a halt. This means that in this particular save point, the overhead of stopping was greater than the work I was going to do, which happens quite a lot, it turns out. So if we run this without the profiler, we'll see the occasional save point operation coming up, and then once the machine warms up, we'll see less and less of them. Okay, but if we do this and we add the profiling, loads and loads and loads of pauses. And you can see that a lot of them are of the kind where, I wanted to stop for 6 milliseconds and I stopped for 6 milliseconds, stopping the threads took 6 milliseconds. The work actually took, what's that, like 6 microseconds. I had 6 microseconds worth of work to do. I stopped everybody for 6 milliseconds. It doesn't sound like a lot. It adds up. The more processes you have, the more lost opportunity you're going to have. So the more throughput you're going to lose to this. 6 milliseconds on 128 processes is over a second of, it's not, but it's nearly a second of user time lost. Okay, now we're going to do better by using Honest Profiler. Right? So I add, this is really terrible because if I don't use a big font, you won't see anything I'm doing, and if I use a big font, then command line gets really long. You can look it up online how to actually set up Honest Profiler, but let's start by just using it. So I set it up to sample the benchmark. The first thing we're going to notice is that there's very little overhead. I don't see the same reduction in throughput I saw before. Right? The other thing we can notice here is that if we add this flag, we're no longer seeing a massive amount of save point time. So we're not seeing all those little pauses coming in. That's great. Are we actually getting a better profile though? Let's see. So Honest Profiler works differently from JVisualVM in the sense that it's an offline analysis sort of tool. You collect the profile and then you go and analyze it. Similar to how Java Flight Recorder works. So I've collected the profile and then, where am I? I'm here, right? I have it here and then I look at the profile and hash map put is top of the stack again. So I thought this was supposed to be better, right? Why isn't it better? The reason it's not better is because the JVM doesn't create debug information for stuff that doesn't happen at save points, because officially no one's supposed to come looking, right? So if they're not going to come looking, why would I bother? So with that in mind, I'm going to make it generate some debug information. Where is the debug information flags? Right, there's 2 flags here that I wouldn't expect you to memorize, but they're in the slides and they're online. basically we're asking for some debug non-safe point information. So you're going to do that. Whee. Right. Going to add these flags here, and life is going to be that much better for it. One hopes. Okay, so has no impact on the performance of this little program. And 10 seconds, it'll just collect the profile, and now we're going to go in here. We're going to have a look, and yay, we're finally actually seeing the method that is the problem. And we can actually see a breakdown by line of code somewhere down here. Yeah, okay, we can see there's several lines in array copy that are taking all the time. Now we actually know where the problem is, right? That's great. We can try and fix the problem. What's the alternative in Java to rolling your own array copy? Using system array copy, right? System array copy should be that much better. So we have a little method here which uses system array copy instead. Where is it? Right, we skipped one demo. System array copy. So let's try and profile that, and A, see if we're getting better performance. B, see if the profile is any good. So instead of 1, we'll replace this with 2. First off, performance is the same. Does that mean we should all be rolling our own array copy methods? No, because of several things. One is system array copy is going to be faster depending on which JVM version you're on and which JVM you're on, how hot the code is, etc. System array copy is a sort of pre-generated, it's called an intrinsic, it gets injected into your code, highly vectorized, optimized code. It's awesome, right? The fact that the JVM can do well on occasion when compiling your code and vectorize it to the level of handcrafted methods like that is great. Don't knock it. This is like awesome work on the compiler team has done, but that doesn't mean you shouldn't use best practices. But it is nice that the JVM got so good that it can actually beat the JVM engineers' handcrafting just by using the compiler. Can we actually see it now in the profile? No. It's gone. Two things happened here. We have first of all, we're not seeing array copy anywhere, right? The other thing is, you'll notice that when we're not seeing array copy, we're only seeing 7% at the top method. We saw like 90-something% beforehand. What happened? Sadly, this is not something Honest Profiler is currently very honest about, but it's getting there. So at the end of one of the sort of log analysis commands you can issue to Honest Profiler, you can see a histogram of the errors that were encountered while sampling. And we can see that of the 1,000 samples we had, 922 couldn't actually be analyzed. And they were unknown Java frames. So we took a snapshot of the stack and we couldn't actually see into it. Now, that's a bit disappointing. So, let's go back to the presentation and see what we can do about it. So, just a few reminders about AsyncGetCallTrace Profiler. So, like I said, Java Mission Control, Honest Profiler, Solaris Studio. If you want to use it, you want to see more, use these flags. You'll get a bit more information, and you'll actually get the benefit of sampling not at a safe point, getting the extra accuracy. They only show you the Java stack, so perhaps people don't realize that, who've done Java all their lives. The JVM is a process with lots of different threads, GC threads. Your Java thread has some sort of C wrapper that's launching it, and maybe you go into JNI methods and you run lots of native code. Java profilers only show you Java code, so you're limited in the scope of what you're seeing. And this is sort of the problem we're seeing here with array copy. It's a little specialized method that whoever done the work on the compiler team failed to transition the thread correctly to a state where you can see the stack. So it's invisible to AsyncGetCallTrace. It's also invisible to GetStackTrace because there's no save point in it. Only on CPU sampled. You can do a little demo showing that if you add a thread sleep somewhere, AsyncGetCallTrace profilers are not going to see that problem. Whereas if I have any sort of blocking issues in my code and I want to see the time spent not doing anything, something like a tracing profiler would do a better job of that because it's looking at wall clock time. It's saying what was the time before, what was the time after. And the fact that you're not on CPU doing anything doesn't matter. GetStackTrace would also sample that stack correctly because if the thread is blocked, I can still get it stacked. With AsyncGetCallTrace, if you're not running code, I can't see you. Okay? You have to watch out for failed samples because otherwise you're looking at a very tilted profile again. Now, that is the experimental part of the show. If you thought this wasn't going well up until now, hang on, it's going to get much worse, right? What is the truth, right? The truth is that it's complicated and there's no line of code, as we discussed, because we've compiled the code. There's also no bytecode anymore. We've compiled away the bytecode. We threw away half of your code because we decided it can be optimized away. You know, we made it into fancy machine code, you know, compacting it and rearranging it and reshuffling it so we can get the best performance out of it. There's only instructions. The CPU doesn't know anything about Java. It just knows how to run instructions. And there's more than just Java running on your CPU. So to see that complexity, we're going to have to use a different set of tools. And most Java developers never actually touch on those tools, and for good reasons. Most of your problems can be diagnosed on the Java level. Not every day do you need to dive into the guts of what's actually happening. But that really depends on your job. So I've worked a lot in sort of low latency environments where people really care about shaving off a few microseconds. And if you care about something at that scale, you're going to have to dig deep and find out what's happening. So let's recap. Where did we get that BCI? How did we come across that bytecode index? Well, in reality, there's no bytecode. There's instructions, and when we sample the stack, we sample the stack of the process. We don't sample the Java stack. And process stacks, if anybody's done an OS sort of course at university, this is what they look like. You have a program counter, you have a frame pointer, you have a stack pointer. Frame pointers are optional. Some compilers don't put them in. Java can now be convinced to put it in. But importantly, there's no, you know, the CPU doesn't know anything about bytecode index or JMethods for that matter. So how do we translate from PC to BCI? PC points to the current instruction. We'll get to that in a second because that's a lie. Not every instruction has a bytecode index. In particular, system array copy, it doesn't have any bytecode. If it's a sort of a runtime method, there's nothing there. Intrinsics tend to not have any backing bytecode. Even your code, if it's optimized enough, I could combine several bytecodes into the same instruction, and then which bytecode are we talking about and which line of code are we talking about? Right? So you find the closest, just like we did with trying to find the line of code, and we blame whoever's nearest. The problem there is that the PC, the program counter, is not that accurate. And this is a dialogue going on the Linux perf user group between Brendan Gregg from Netflix, who's the big sort of performance guru, talking to Andy Klein, who's the Intel representative on the perf tool, And Brendan is saying, I think Andy mentioned it, that instruction profiler is no longer reliable. And Andy is saying, well, it never worked, basically. Why doesn't it really work? The reason is, it's described as skid. Part of the problem is that, again, reality is complicated. CPUs, I'm not sure people realize that CPUs for a long time now, they don't execute a single instruction. They execute maybe 4, 5, 6 instructions in parallel. They have loads of instruction parallelism going on under the covers. So when I say this instruction is running, and I only have one instruction I can blame, I'm just lying to start off with. I'm randomly picking one of those instructions that is actually running. The other thing is, the CPU can speculate ahead and sort of execute stuff that it can't actually execute yet. So if I load something from memory, it's going to take a while to come in. There's an if dependent on that load. I'm going to speculate past it. I'm going to say, you're probably going to say yes. I'm going to run this code, and when you come back and you do say yes, I'm going to say, ha! I've already done that. Because I knew you were going to say it. If you come back and say no, I'm going to say, well, let's do something else. I was waiting anyway, right? And the last thing is signal latency. So when I ask for the program counter, it's going to take time for the CPU to actually come back and tell me this is the program counter. All of this adds up to slight inaccuracy in the program counter identification. There's really very little you can do about it, but it's worth knowing about. And we'll get to that in a second. The blamed instruction is often shortly after where the big cost lies. If you look at sort of profiles of assembly, you will see that quite often. It's not too bad when you're looking at the assembly. So I love that quote. Yeah, 60% of the time it works every time. Definitely. It's as good as it gets for Java profilers because we want to tell you about lines of code. We have to approximate. Mostly good enough. You have to look for other suspects nearby. Nearby is sort of a problematic word. Why is that? Live demo. Woo! Yeah, okay. I'm more excited than the audience. That's never a good sign, is it? Okay, so we saw that with AsyncGetCallTrace we can't actually. Let's go back to the beginning. Okay, so we had that. We're going to run it for a while. Okay, we're going to use an exotic tool called perf map agent, and that's using the perf profile. It's a native profiler that everybody who's doing any sort of profiling on Linux should be aware of, and mostly native application developers use it. The reason Java guys don't use it is because it doesn't work for Java. The reason it doesn't work for Java is because the Java stack is opaque and it doesn't have the frame pointer, so perf can't tell what you're running. The other thing is that perf is sort of built on the assumption that your code is statically compiled. It's compiled ahead of time. So I can do offline some sort of processing to find which method you came from. But in Java, I'm just making it up as I go along. You know, one method might not be the same in the next run. So perf just has nothing to look at and it comes back and says, well, I don't know what you're running. Right. So I'm going to look at JPS again. Here's our forked main, and here's, I'll have a look at the flames just now, which is even better. I'm really excited about flames. I think they're the best thing. We'll have a look at them just now. So, perf Java top, it requires you to be root, and there we go. You will notice that I'm not seeing array copy. But what I am seeing is the method above it. The reason we can't see anything is because, yeah, that's better. Can people see this? Okay, that just about fits on the screen. And you can see that the benchmark method here is showing up. Very hot, 97%, excellent. But I wanted to see array copy. Why isn't it showing me array copy? Well, for one thing, by default, it won't show you any inline methods, which is, in a way, the truth. Why is it the truth? Inline methods stopped existing. The compiler took them away and shoveled them all together and made something new. And that can get very confusing when you're talking about nearby code, because if I have loads of little methods and they all get inline together, they might be one instruction under the next. But if I looked at the Java execution tree, they're like miles apart. They're in two different classes, way further than the actual method that's getting executed. So perf map agent is telling the truth. The only method that is running is that top method. There is no other method. The other methods are a figment of my imagination. But I did tell it to show me the figments of my imagination by using this. So I gave it some options and I did tell it to unfold the underlying methods. Why can't it show me array copy that is inline? And the reason is because there's no debug information again. So to make this work, let's bring debug information back. I've just run over the slot, but hey, you don't have anything better to do you? Right. So let's profile the first method, and we have a look here. We need to do JPS again to find what it is we want to profile. There we are. And now, because it's inlined, it's sort of fell off the screen, but there we go. So this is closer to the truth, because it's telling me, yes, this method is running array copy, but it is running as an inlined method in hashmap put is to blame. Okay, that is the truth. Looking at the stack and saying array copy is running is ignoring the fact that it's running in a particularly limited context. Now, for array copy, it doesn't really make much of a difference, but consider methods where you maybe have some flag you pass in, and the first thing you do is say, if false, return, right? If I inline that method into a context where all you do is pass in false, that method is just going to disappear. You're never spending any time in it ever again. Alternatively, if you're doing just a little bit of work in it, it's not that you're never hitting the code that's on the other side of the if. That code is not there. It's the compiler threw it away because there's no way it can run. And that's the sort of problem with the statement, look for something nearby. Once you start inlining methods and shoveling them around like that, nearby means nearby in the compiled assembly. And that is quite a difficult sort of thing to look at most of the time. Not so much, did I? Where is it? Yeah, okay. The other thing we wanted to look at is the second version with array copy. And this time, lo and behold, we will be able to see the copy. And perhaps surprising to anyone who hasn't looked into the guts of the JVM, there's several copy methods. This one is the disjoint one because we're copying two different arrays, one into the other. If you're copying arrays that are overlapping, then you'll get another method. But we can see that, and it is a separate method that's getting executed as opposed to what happened before. This intrinsic is getting replaced with a method call. It's not getting inline. The implication is that maybe if we copied very small arrays, using system array copy will not be a good decision there. But that's a separate one. I'm going to show you one more tool if you're really sort of hardcore looking at a problem that you just have no idea what the hell is going on. And this will let you confuse yourself further, which is always good. So again, what is the truth? The truth is we're running assembly. Because most of the people using JMH initially were people like me, sort of performance engineers for the JVM, people will come along and say, I wrote this really trivial benchmark and I have no idea what the fuck is going on. Right? I did something trivial. JVM optimized away everything I was doing and it takes no time at all. Can you tell me what happened? And then with very, very small benchmarks, you often end up looking at the assembly. So Mr. Shipilev, Alexei Shipilev from the Oracle performance team added a very nice feature to JMH, which is perf ASM, which sort of lets you look at the assembly with everything, all the ugliness that comes with it, in a very neat and handy sort of way. So we're going to shove it into less, and we're going to look at the truth, or as close to the truth as we can get. Right, takes a while to run. After that, it pretty much concludes the show for today. So we can see here that, okay, we're in the method. After inlining, it's showing one thing, then it's showing us all the regions. I won't go through the whole thing, but here we are looking at glorious assembly. And if you like this sort of thing, then you're weird. But if, what are you doing programming in Java? If you like assembly, just, get on with it. But what we see here is that, inlining happened and the method that we thought we were running, array copy, is there no longer. And we see per instruction attribution of cycles. This is great stuff when you're looking at very, very low level problems, and some people do look at low level problems. This is the way forward for looking at those problems. It only works if you frame your benchmark as a JMH benchmark at the moment. There's other tools that let you do this sort of drill down. Sometimes it's the right tool for the job. Most of the time, you're better off starting higher up the stack and finding out where the bottlenecks are. But that is what the truth looks like. Okay, takeaways from here. You have to know your profiler. If you don't know your profiler, you wouldn't be able to know when it's lying to you and when it's not able to tell you where the bottleneck is. A good sign of that is when you see a bottleneck in a profiler and you change that piece of code and the bottleneck just is, the performance is the same and the bottleneck just moved a little bit. That's a sure sign that the profiler is just telling you something completely useless, or you're misinterpreting it. The other thing is, there's no perfect profiler. I was going to do it, but you'll just have to trust me on this. Again, if you run in the interpreter, perf map agent just has no idea what's happening. So it's all just one interpreter block to it. So perf map agent, while great, still has blind spots, and every profiler will have blind spots. So maybe try a few. If you're looking at a particularly hairy problem, try some other combinations. Try an unbiased profilers. They're not as hard to come by these days as they used to. Java Mission Control is expensive to run in production, I'm told, but you can run it on your developer machine and see if you can spot anything unhealthy going on. And it's more accurate than JVisualVM for this sort of profiling. That's it. I don't have a slide for questions, but I am sure that if you have them, I'll be happy to answer them. Any questions? Going once, going twice. I ran 10 minutes over. Do you want coffee and breakfast?
Yeah. Thank you very much.
Thank you.
So, yeah, we kind of run a little bit over. It's not a massive trace time. I think we can all be back here for 25 past 10. So it's just coffee, smoke, biscuits, whatever else. And I'll see you guys back here at 25 past.
Yes.